we've seen two cases where undetermined coefficients, the method of undetermined coefficients, is not likely to be helpful. Let's think about what we might do to get around this problem. Suppose we have an equation, just any old equation, second order equation. We don't have to have constant coefficients, but it's a non-homogeneous second order equation. We might not know how to solve the characteristic equation depending on our P of t and Q of t functions, but let's assume it is something where we can solve the characteristic equation. So we're going to assume that we've got some fundamental set, y1 of t, y2 of t, some fundamental set of this equation, the homogeneous equation with the zero, so that our characteristic solution is going to be a linear combination, c1 y1 of t plus c2 y2 of t, a linear combination of the two functions in our fundamental set. Now, this characteristic solution has two arbitrary constants. We call those constants parameters. So the parameters of our characteristic solution are c1 and c2. And what we're going to do is we're going to assume that there's a solution to the non-homogeneous equation where instead of using constant parameters c1 and c2, we can use two functions in place of c1 and c2 and somehow manipulate this equation into a solution. So let's try a particular solution. Yp equal u1 of t, y1 of t, plus u2 of t, y2 of t, where the u1 and u2 are functions of t that have replaced our constants here. Now, it makes a certain amount of sense that this is at least a plausible thing to do, because by making these functions of t, we broaden the range of these solutions. We get a much more a much broader and more general set of solutions by replacing the constants with variable functions. There are other reasons that this works, and you'll see how this works before too long. Now I'm going to give you the end result that comes from this assumption, and then after working a couple of examples, we'll come back and see why the end result works. Just how we proceed from this to the end result. It isn't too awfully difficult, although it is somewhat challenging. So if we do this, we find that we can get an equation for u1 prime of t and u2 prime of t in terms of y1 and y2 and g. Now more strictly, in terms of y1, y2, the derivatives of y1, y2, because remember, y1 and y2 are functions of t, and of course g is a function of t. The equation to which I refer is a matrix equation. And it's not too complicated. It's simply y1, y2, y1 prime, y2 prime, multiplied by u1 prime, u2 prime, equals 0g. And this matrix equation could also have been written as a set of simultaneous equations. y1 of t, u1 prime of t, plus y2 of t, u2 prime of t, equals 0, just using the common rules of matrix multiplication. And the second equation I'm writing, that's very similar to the first, except now we have the derivatives of u1 and u2, and instead of 0 on the right hand side, we have g on the right hand side. It turns out that the matrix equation is actually easier to solve because there's an easy way to invert a matrix. Matrix equation is easier to solve, but the simultaneous equations could be solved just as well.